Hello, everybody. I want to introduce the natural logarithm and the exponential function. Um, you know that sine and cosine are defined by means of the unit circle. For the definition of ln of x, we use another geometric object, a hyperbola. The equation of a hyperbola is y equals 1 over t. Now, for any positive number x, I want to define the natural logarithm ln of x. This will be the shaded area here. More formally, ln of x is this integral. Usually, the lower bound of an integral here, 1, is smaller than the upper bound here, x. However, if x is between 0 and 1, this is not true. In this case, we simply flip the 1 on the x and put a minus sign in front. This means that the areas between 1 and 0 count as negative. This may seem odd at first, but it is like the relation of the position of a moving object and its velocity. Going backwards means negative velocity, and here integrating backwards means negative area. In red, you see the graph of ln of x. Its form should be obvious from the definition. For instance, if x is 1, then there is no area, so ln of 1 is 0. If x increases starting from 1, you create some area, and so ln x increases, becoming flatter and flatter because 1 over t becomes smaller and smaller. If x is smaller than 1, the area counts as negative, hence ln of x is negative. Now, what happens if x goes to infinity? One can show that the area below the hyperbola is infinite, so ln of x goes to infinity, but very slowly. Now, the hyperbola is symmetric to the angle bisector, y equals x. So the area below the hyperbola between 0 and 1 is infinite as well. This means that ln of x goes to minus infinity as x goes to 0, and very quickly. In short, we have this. In particular, ln of 0 is not defined. The domain of the natural logarithm are all positive numbers, and the range of ln of x are all real numbers. Here's an application which shows that there's a relation between prime numbers and the natural logarithm. There is no explicit formula for prime numbers. The prime number theorem shows us how to count prime numbers. Pick any number x. We want to count the number of primes at most as large as x. Well, this is a function which is called pi of x. This is unrelated to the number pi. For instance, if x is 10, then pi of 10 is 4, because there are 4 prime numbers smaller than 10, namely 2, 3, 5, and 7. Now, there's good news and bad news. The good news: there is a formula for pi of x. Just divide x by ln of x. The bad news is that this is only a so-called asymptotic formula, as you can see by this tilde here. It just gives an approximation, like, say, Riemann sums approximate areas, which gets better as x gets bigger. Here's an example. The number of primes smaller than 1 million is this. The actual value is this, which is 8.5% off. Disappointing, is it? It gets better if the powers of 10 become larger. For instance, pi of 10 to the power of 25 is only 1.8% off. Here's a better version of the prime number theorem due to Dirichlet, a German mathematician of the 19th century. It involves the logarithmic integral Li of x, which is another example of a function defined by an integral. Note that it also involves the natural logarithm. Li of 1 million is a much better approximation. The absolute error is only 129 and the relative error is 0.1%. In the next video, I'll explain the characteristic property of ln of x and introduce the exponential function.